To understand the scale of modern engineering, compare the Great Pyramid of Giza to the Burj Khalifa. The modern tower stands more than 5 times taller than the ancient wonder. This gap in height exists despite the fact that ancient societies were clearly capable of architectural miracles, solving complex geometry and logistical problems that would still challenge us today. Take Göbekli Tepe. 11,000 years ago, humans were already carving and moving T-shaped stone pillars weighing several tons with surgical precision. And yet that record for height barely moved for millennia. The Great Pyramid remained the tallest structure on Earth for over 3,800 years, only losing its title to the towers of Lincoln Cathedral in the 14th century. If humanity possessed the raw intellect to build stone henges and massive Roman aqueducts, what specific physical boundaries kept them pinned to the ground for so long? The ancient height ceiling resulted from a direct encounter with the unforgiving laws of physical science. The first barrier is the material itself. In construction, you deal with 2 forces: compression, where you're squeezed, and tension, where you're stretched. Stone handles compression well, but it is incredibly heavy. When you stack it too high in a thin column, the weight of the top eventually exceeds the strength of the bottom, crushing the base. Ancient builders solved this by going wide. By shaping their tallest structures like pyramids, they distributed that massive weight across a wide footprint rather than a single point. This limitation stood until 1885, when Chicago's home insurance building rewrote the math of how a structure supports its own weight. Hidden inside was a load-bearing steel skeleton. For the first time, the weight wasn't carried by the stone walls, but by an internal metal grid that could handle both compression and tension. Structural steel provided the breakthrough needed to move beyond the pyramid shape and build vertically without the base collapsing. But as buildings get taller, gravity becomes a secondary concern. The atmosphere becomes the primary enemy. At extreme heights, wind behaves like a physical hammer. Modern towers like the Burj Khalifa use a tapering Y-shaped design to break up wind vortices that would otherwise vibrate a square building to pieces. Even if an ancient builder mastered steel and aerodynamics, they would still be left with an unusable stone shell. Without the safety elevator, patented by Elisha Otis in 1852, a skyscraper is just 160 flights of exhausting, impractical stairs. Then you hit the lifeline problem. To make height habitable, you have to mechanically pump water hundreds of meters against the pull of gravity. You need a high-voltage electrical grid to power internal climate control and lighting for floors that never see the sun. And you need deep foundation soil mechanics to ensure the thousands of tons of steel don't sink into the earth like a stone in water. Without this overlapping stack of modern utilities, a tall building is just a monument, beautiful to look at, but impossible to live in. Finally, we have to look at the motive. Ancient cities didn't have the extreme urban land costs that drive modern builders to pack thousands of people into a vertical column. Modern high-rises are designed to maximize hollow, usable floor space. The pyramids were designed for mass, solid, permanent tombs built to survive for eternity. Ancient engineers mastered the specific technological frontier of their era, the precise movement and stacking of massive weight. A skyscraper is different. It requires the simultaneous convergence of structural steel, wind engineering, vertical transport, electrification, pressurized plumbing, and soil mechanics. A modern skyscraper functions as a complex, vertical machine. Ancient builders didn't lack the genius to build one. They simply lived in a world where those 6 technological revolutions hadn't happened yet.